all our previous lectures in engineering mechanics, we primarily saw how to compute the various forces and the moments for concentrated loads. When we have distributed loads in a system, then we have to find their equivalent in order to evaluate the moments due to those distributed forces and their effects on the equilibrium of the body. So, we will see certain procedures to compute the points of concentrated load that can be said to be equivalent to the distributed loads. So, one such measure is the centroid or the center of mass. So, we will discuss about them and how to compute these values for various shapes in this lecture. So, for your reference, this is module 6, lecture 13 of engineering mechanics course. Let us see what kinds of distributed forces occur. We very well know that gravity acts on all the constituent parts of matter, and thus it is in fact a distributed force. So, weight of a body is in fact an distributed force. So, here the distribution of the force is throughout the volume of the body. Every part of the body experiences the gravity, and thus the weight of the body is in fact a distributed force over the volume. Next, we have some examples of force distributed on surfaces, like the water pressure on the walls of the dams or the walls of the pressure vessels is in fact a distributed force on surface. So, pressure is an example of force distribution on a surface. Then we have also force distribution on line or on curves. We have examples like the loading of the beams that we have already seen. So, we see that the dimension, like here is 3 dimension, here it is 2D and here it is 1D, and we have the force distribution and examples for all these cases. So, let us see how to compute this mass center or equivalent points through which we can assume the mass to be acting in order to compute the weight of the system or the moment of the weight of the body with respect to, let us say, some coordinate frame. So, let us consider a rigid body which is having uniform density, say rho. Here in this picture you see one such body, and it is acted upon by gravity. This body is acted upon by gravity. Let us fix some reference frame, let us say O, X, Y, Z. If we consider a differential mass element of this body, say this small cube that you see over here, the mass of this element is rho dV if dV is the volume of the element, and the weight is gravity times the differential mass, which is equal to g times rho dV. And this vector shows both magnitude and direction of this weight of this differential element, that is dW. So, if we consider the object which has dimensions comparable to, say, the size of the earth, then if we consider a differential element in this body, and if say this is the center of the earth, then we know that gravity at any point acts radially towards this center, and so this vector, which is dW, is in fact acting towards the center of the earth, say CE. But if we consider the size of this body to be small, then we can assume that all these vectors are in fact parallel. In this case, or in reality, these vectors are not parallel, but if the size of the object can be considered to be small, then these vectors can be assumed to be parallel. So, that is the assumption that we make, that if we assume the object size to be small and is close to the earth's surface, then we can assume these directions to be vertical, and so all these differential elements have this weight dW, which is parallel to the z axis, and it is equal to g times rho dV, where g is the acceleration due to gravity and rho is the density and dV is the volume. So, if we assume the size of the object to be small and close to earth, then the assumption that all these vectors dW are parallel is valid. So, with this assumption, let us see how to find the resultant of all these forces, that is dW. So, the resultant of these forces, if we say is W, is equal to summing up all these differential weights over the volume V of this object. So, which is equal to integral over the volume of G rho dV. So, this expression gives the resultant of all these differential weights. But now, we have only equated the forces to find the resultant. Now, we have to find if the moments are also equal, so that we can find the point of action of this equivalent force W. So, let us consider the location of this differential element dV at x, y and z with respect to this reference, that is O, x, y, z. Then if we are interested to find the moment of these differential weights with respect to this axis OX and equate it to the moment of this concentrated load W, which let us say acts through a point G. The coordinate of this point G, let it be x bar, y bar and z bar with respect to this frame of reference. So, if this concentrated load W has to be equivalent to all these differential weights dW, then sum of the moments of these forces about say this axis OX has to be same as the moment of this vector W with respect to this axis OX. So, we write that, say if we take the axis OY, then we can write x bar, which is the moment arm for this vector W with respect to this axis OY, times W is the moment, should be equal to the summation of the moments of all these vectors dW over the entire volume. So, integral V x, which is the moment arm for this vector dW, which is g times rho dV. So, from this expression we can find what is x bar, or the location of the coordinate for the concentrated load with respect to the axis OY. Similarly, we can sum the moments with respect to the other axes, that is say with respect to OX, in which case the moment arm is y bar, and if we take the axis for this OZ, then we have this moment arm of z bar. So, we can write these additional equations, that is y bar W equal to integral V y times g rho dV. From this expression we can find what is this y bar, or the location of this vector with respect to this plane OXZ, and same way z bar W equal to integral V z g rho dV, which gives this value z bar, or the location of this point with respect to this plane OXY. So, from these expressions we can now locate the point x bar, y bar, z bar, which can be considered as the point through which the equivalent load or the equivalent weight W acts, and this point is known as the center of gravity for this body, and weight of the body is also defined by this integral dW. So, now let us see how we can extend this discussion to find other centers, that we call it as center of mass and centroids. To find this quantity center of mass, which is nothing but a point through which all the differential mass elements act as a single quantity, that is say the mass of the object. So, it can be said to be the equivalent point through which the complete mass of the body is assumed to be concentrated. let us assume that uniform gravity acts throughout the object. In that case, this quantity g can be taken out from the integral. So, we get this g times of m as the weight is equal to g times of integral v rho dv. So, the quantity has been defined in this way, from which we remove these common terms and we get this expression for m as integral v rho dv, or it is nothing but the integration over the volume of dm, which is nothing but rho dv. And now we can take the moments of this mass and equate it to the moment of these differential mass elements, that is dm. So, we have x bar m is equal to integral v x dm, which is rho dv. So, from this expression we get the coordinate x bar, or the location of this point through which it is assumed that the complete mass m acts with respect to, say, the plane O z y. In the same way, the other two coordinates, that is y bar and z bar, can be computed by taking the corresponding first moment of this mass. So, this coordinate x bar, y bar, z bar defines the center of mass. So, if the gravity is acting throughout and it is same, then we have the mass center and the center of gravity as the same location. We can extend this discussion to define this centroid, or the point where we can assume that the complete volume is concentrated. So, if we assume that the body is constituted with uniform density material, then this rho can be taken out of this integration and can be cancelled, and thus we have the volume of the body as integral over the volume dV, the differential volume of these elements, and the coordinates of the first moment are x bar v is equal to integral over v x dV. In the same way, the other coordinates, that is y bar and z bar, are defined. So, these coordinates x bar, y bar and z bar are the centroids of this volume. So, from these discussions we see that if we assume the density to be uniform and the gravity to be the same throughout the volume of the body, then the center of gravity, the center of mass and the centroid of the volume are all located in the same place. Let us discuss and extend these derived quantities for thin plates. For thin plates, the thickness can be assumed to be uniform and equal to T. So, the differential element dV is equal to T times the differential element dA. So, if I consider say an element here whose thickness is T, then if dV is the volume of this differential element, it is equal to T times or the thickness of this body times dA, which is the differential area of this element. So, we write dW or the weight of this element as g times rho times dV, which is T times of dA. And if we compute those quantities, we will find that if other things remains constant, that is it is a homogeneous material. So, rho is constant and gravity is also acting constant, and it is a thin plate or a uniform plate, then T is constant. Then we will see that the centroid C of this area coincides with the center of gravity and center of mass of this plate. So, we have the area of the plate as the integral of this dA, and the first moments are x bar A equal to integral x dA, and this quantity integral x dA is known as the first moment of this area with respect to the y axis, because we are taking this momentum with respect to this y axis. So, this quantity is known as the first moment of the area with respect to y axis. Same way, the coordinate y bar is defined and is known as the first moment with respect to the x axis. So, these quantities, that is x bar and y bar, can be found for various shapes a priori and tabulated, and engineers generally use these values for their computation. That means, the location of the mass center or the center of gravity is same as the location of the centroid, and this is useful for various computation. Let us further extend this discussion to uniform wires. So, if you consider a small element in this wire, the weight of this element is dW, which is equal to g times rho times, if A is the cross section area, let us assume that this is the differential element and it is having uniform cross section throughout this wire. So, let us say A is the area of cross section of this element, which is constant throughout this wire, times dl or the differential length that we have taken along this wire. So, we have dw as g times rho A dl, and if we integrate this, we find the quantities, that is, if we take out these constants like g and rho and A from the integration, because we assume homogeneous material and small objects. So, g is also constant, and we are additionally assuming a wire of uniform cross section. So, this A is constant. So, the integration simplifies to L, which is the length of the wire, equal to integral dl, and we have the first moments as x bar L equal to integral x dl, which is the first moment of this curve with respect to the y axis, and we have this quantity y bar L equal to integral y dl, or the first moment of this curve with respect to the x axis. So, now we have seen in general how to compute the coordinates of the centroids or the mass center and the center of gravity. We will discuss little more the discussions on finding the centroids and mass centers for the case of plates. For laminas or plates, the centroid lies on the line of symmetry. This can be found from this example, where we have taken this plate or lamina which is having a symmetry with respect to this axis, say OY. We have already seen that the centroid is defined based on the first moment of the area. So, if we take any differential element, say dA, so the first moment of this element with respect to this axis OY is nothing but x dA, and we know that we define the centroid x bar, and if A is the total area, as the sum of this value x dA for the entire region. So, we see that if symmetry exists for this object, then for every element dA which is at a distance of x from this OY, we have a corresponding element dA prime which is at a distance of minus x. So, this quantity can now be grouped as integral x dA plus minus x dA prime, and for every element that we find, we have a complementary element dA prime which is having the same moment arm. So, these two quantities cancel out and this becomes 0. So, obviously area is not 0. So, this quantity x bar has to be 0. That means, the moment or the first moment of this area with respect to this OY is 0, that means it lies on the same axis. So, it can be proved that the centroid lies on the line of symmetry by considering this first moment. Here you see another example where we see that this geometry or the shape of the plate has a symmetry with respect to this axis B prime. So, if we shift our axes, let us say our y and x, and compute the moments, then we can find an element at P and P prime having the same moments, say x and minus x. So, if we sum up, the first moment of these differential elements, they sum to 0, and we find that the coordinate x bar has to be 0, that means it has to lie along this line. So, this is valid for any shape which is having an axis of symmetry. So, if we have two axes of symmetries, then the centroid lies at the location where these lines of symmetries intersect for the lamina. So, here you see an example where this shape has symmetry with respect to OY or the y axis as well as with respect to OX. So, if we try to find the first moment of this area with respect to this axis OY, so we have x bar A equal to integral x dA, and we see that these elements have a corresponding element which is having the same area. So, the integral x dA can be said to be constituting of integral x dA minus the complementary elements, that is dA prime, and this quantity being 0, we have x bar as 0. And similarly, if we take the other integral, that is y bar A equal to integral y dA, we again see that for each of this element we have the complementary element dA prime, and this quantity is 0, and thus we find y bar is also 0. So, we see that the centroid is located at x bar y bar, which is 0, 0, which is nothing but this origin, and we see that this origin is nothing but the intersection of the lines of symmetry, and this is valid for any shape. Let us consider this triangle. It has in fact 3 axes of symmetries. We consider these two, that is D D prime and B B prime, and the intersection of these two lines of symmetry is at C, and this discussion whatever we have done can be extended to this by considering, let us say, any element, any differential element. It is possible to find a corresponding element, and thus the sum of the moments of these elements is 0 with respect to this axis, and same way it is possible to find elements which are having the same moment with respect to D prime, and thus if we sum them it becomes 0, and thus they lie along this axis. So, if the mass center or the centroid has to lie along this line as well as along this line, we see that the possibility exists only at the point of intersection, that is C. So, this discussion holds good for any shape, and if we have the lines of symmetries, then we can advantageously use it, and we can only find the other coordinate that has to be found by, let us say, the integral. So, for shapes which are very common for engineering application, we have these centroids defined. Like for this picture, we have the centroid located along the axis of, that is the angle bisector, and only we have to determine this y bar, which is in this case, if you find the integral, it will be h by 3. And same way, let us consider another example like a semicircular lamina, and since we have one axis of symmetry, we can say that C or the centroid will lie along this line, and we can only find the location of this C with respect to this diametrical line. If r is the radius, and if we integrate it, we can find this quantity y bar as 4r by 3 pi. So, for common shapes, these values, that is the centroids x bar and y bar, are tabulated and they are available for use for various computations. Generally, the shapes that we use are composite shapes which constitute a combination of these simpler shapes like the circular lamina, the rectangular lamina, or the triangular laminas. So, if you are interested to find the mass center or the centroids or center of gravity for these complex shapes, and if it is possible to divide them into simpler shapes for which the centroids are defined, then the problem of finding the centroids is made easy. So, let us see this. The areas of the centroids of various shapes are known. So, if a flat plate can be divided into several of these shapes, then the coordinates x bar and y bar of the center of gravity can be determined from the coordinates, that is x1 bar, x2 bar, etc. of these various parts. So, let us see this example. We have this shape, complex shape, and we are interested to find the location of its centroid or mass center, that is these quantities x bar and capital Y bar, and we find that this shape can be decomposed into, let us say, one rectangle and two triangles, and for these simple shapes the location of the mass center is known, that is, let us say, G1, G2 and G3 are the location of these mass centers, and if W1, W2, W3 are the weights of these plates, then the first moment of all these quantities with respect to, let us say, this axis OY, the sum of all these moments is equal to the moment of this force, single force, which is nothing but sum of W1, W2, W3 into the moment arm. So, that is what we have, x bar sigma W is equal to sigma small x bar, which is nothing but the location of the centroid, mass center and center of gravity if we assume homogeneous materials, and same way y bar sigma W is equal to sigma small y bar W, and from this we have x bar sigma A equal to sigma x bar A and y bar is equal to y bar sigma A is equal to sigma y bar A. So, in this way it is possible to find the location of the centroids of plates if they can be decomposed into simpler shapes. Let us take one example to find the centroid of a plate which can be decomposed into simpler shapes. Here you see a lamina which is composed of certain annular hole region and let us say composed of a triangle and a rectangle. So, this shape from our understanding it can be decomposed into a rectangle, a triangle and a semicircular lamina, and we have to remove from the sum of these areas this area corresponding to this circle. So, now we see that this complex shape can be decomposed into simpler shapes for which the centroid is known. So, we have this rectangle whose centroid is located, obviously this rectangle has two axes of symmetry. So, it is located at 40 mm from x axis and 60 mm from y axis. Let us take this triangular lamina. We know that the centroid is located at a distance 1/3 height. So, in this case the height is 60 mm. So, it is located 20 mm below the x axis, and if we consider this semicircular lamina, it has an axis of symmetry. So, its centroid lies at 60 mm from y axis, which is equal to the radius of this semicircular lamina, and it is located from its diametrical line at a distance of 4 r by 3 pi, which is in this case 25.46 mm. And for this circle the centroid obviously lies at the center of this circle, which is 80 mm from the x axis and 60 mm from the y axis. Knowing these quantities, we can find the first moment about the required axes, let us say x and y axis, and from which we can find the first moment of the sum of all these areas. So, we can write, let us say for x axis I can write x bar A is equal to, if I say this as the area of the rectangle and I have the location of the centroid with respect to the y axis as 60 mm. So, 60 times let us say area of the rectangle, which is 40 times 60 plus 40 times area of the triangular lamina plus 60 times the area of the semicircular lamina minus 60 times the area of the circular lamina. And since we know all these quantities can be computed from the geometry, and we also know the total area A, which is area of the rectangle plus area of the triangle plus area of the semicircular lamina minus area of the circular lamina. We can find this quantity x bar can be determined. So, now let us move on to discuss how to find these centroids by the method of integration. We have already considered that if I have a area and I am interested to find the centroid of this lamina or the plate, then I consider a small element, say dA, which is equal to dx times dy, where these are the dimensions of these elements. So, I find the equivalent x bar A as integral, let us say x dx dy, where A is equal to integral dx dy, and this is a double integral, because you have to integrate for the limits in x and y. So, for curves, let us say if I consider this curve and I am interested to find the centroid of the area under this curve between the limits, say x1 and x2, then I consider this differential element dx dy, and I can find this quantity. Now, I can avoid this double integral if I consider, instead of a element whose dimensions are dx dy, I consider this rectangular strip whose dimensions are dx and y. For a small element, I can say that this is equal to a rectangular strip whose dimension is y. So, if I have the equation of this curve defined as, say, y equal to some function of x, then I can define a series of such rectangular strips and integrate them. So, now the double integral has been converted to a single integral, where if I consider these elements, I know that the centroid of this rectangular strip will lie here, which I may call it as, say, y bar of the element. So, now I can sum these quantities to find the centroid of the area under this curve. So, by taking suitable elements, one can avoid these multiple integrals. Let us see some examples. So, you can either consider thin rectangles as shown in this example, or you can consider other forms of thin strips also. So, here you see one example where we have this curve and whose equation is known, and we are interested to find the centroid of this area, that is the area under this curve. So, let us take this thin element, which is a vertical strip whose centroid is located at y bar element and at x bar element for the axis OY and OX. So, we can write x bar A as integral x dA, which is the double integral if we take a small differential element of this form. But now, since we have taken this rectangular element, it becomes a single integral with x bar of this rectangular element times dA, where dA is the area of this thin strip. And in the same way, we can define this y bar. We know that for this thin strip the area is y dx. So, we have this quantity as integral xy dx, where y is a function of x again. So, now it becomes a single integral in x. The same way here we have, for determining y bar, it is integral y by 2, which is this distance, times y dx, which is the area of this element. Again, now this is a function of x, because we have y as a function of x, and so it is again a single integral. We can also take other forms of elements, like in this example we have a thin triangular strip which can be swept in order to approximate this area, and so we can define the centroids by taking these elements, where dA is the area of this element, and same way y bar can be defined as integral 2r by 3, which is the location of this centroid with respect to this coordinate, and we have this area as 1 by 2 r square d theta, where theta is the angle, d theta is the angle swept by this small triangular element. Let us consider one example to completely illustrate this procedure. So, we have this curve y equal to kx square, which is a parabola, and we are interested to find the location of the centroid. So, to proceed with this problem, first we have to determine this value of the k. So, we find that by substituting the end condition, that y is equal to b when x is equal to a, and from that we find this value of k, and thus the equation of this parabola as y equal to b by a square x square. Now, we find the total area. So, we have this differential element dA, which is considered as a thin vertical strip, and we integrate this between 0 to a, and we have the area as AB by 3. Now, in order to find these first moments, we consider this element which has the location of the centroid as y element, which is y by 2, and x element, which is nothing but x itself. So, Qy which defines the first moment of this element, and the sum of all these first moments is the first moment of this area with respect to y axis, and it is found as a square b by 4. So, here you will see that y xy dx is the first moment of this small elemental area, and it is integrated between the limits 0 to a. Similarly, we can find the other moment that is the moment with respect to x axis. Once we know these moments, we also know the area and we can find the coordinates, that is x bar and y bar. So, we have area as well as qi found, and so we can find this x bar, and it is found as 3 by 4 a, and similarly we can find y bar as 3 by 10 times of b. So, this example illustrated the method of finding the centroids by integration.